Have you ever looked at the universe, from a swirling galaxy down to the very cells in your body, and just thought, wow, it's so complex? Well, what if I told you that a huge chunk of that complexity is actually run by just a handful of profound and kind of hidden rules? And these rules aren't about single particles doing their own thing. Nope. They're about how particles behave when they get together in massive crowds.
So, to get what I mean, let's start with a few puzzles. Things you might have wondered about. First up, a real classic. Why is the sky blue? We all know it is, but what's the deep-down physics behind that specific color up there?
Okay, now let's zoom way, way out. Picture a star, maybe like our sun, after it's burned through all its fuel. Its own gravity is just immense, and it starts crushing the star down, trying to squeeze it into a single, infinitely tiny point. But for a lot of stars, that doesn't happen. Something pushes back, stopping the collapse and leaving behind this stable, glowing ember we call a white dwarf. What is that mysterious force?
And for our last puzzle, let's go totally microscopic. You mix a couple of chemicals together and they react, right? They start making new stuff, but they don't just keep reacting forever. At some point, they stop. They reach this perfect balance, this equilibrium. How do they know when to stop?
So get this, a question about light, a question about stars, and a question about chemistry. They all have the exact same root answer. It all comes down to the bizarre collective behavior of trillions upon trillions of tiny particles, the hidden physics of quantum crowds. So the master principle, the one big idea driving all of this, is nature's constant search for balance. You can think of it like a cosmic drive to find the most comfortable, stable state possible.
In physics, we call this big idea Helmholtz free energy. Now that equation might look a little scary, but the concept behind it is actually pretty beautiful. Basically, every system in the universe is trying to do two things at once. First, it wants to have the lowest possible energy, the U. That's like kicking back on the couch, a low-effort state. But at the same time, it also wants to have the highest possible randomness, or entropy, the S. The universe just loves a bit of chaos. The most stable state, the one nature's always aiming for, is the one that minimizes that free energy by finding the perfect compromise between those two drives, low energy and high chaos.
But here's where it gets really interesting. How a system finds that perfect balance depends completely on who's in the crowd. Because in the quantum world, not all particles play by the same social rules.
In fact, we can pretty much divide all the fundamental particles in the universe into two major groups. You've got the antisocial ones, and you've got the supersocial ones.
On one side, you have the fermions. These are the antisocial particles. Think of them like cars in a parking lot. Every single car needs its own parking space. This rule is the famous Pauli exclusion principle, and it applies to electrons, protons, and neutrons. The very stuff that makes up all matter. Then on the other side, you have the bosons. These guys are the life of the party, the social butterflies. Photons, which are particles of light, are a perfect example. They are like a crowd at a concert, all trying to cram into the very best spot right by the stage. They have zero problems piling into the exact same quantum state.
And this antisocial rule for fermions? It has massive consequences. Imagine you're adding electrons to an atom. The first one will happily take the best spot, the lowest energy level. But when the second one shows up, that spot is taken. The rule says, nope, you can't come in here. So it's forced to take the next energy level up. And a third is forced higher still. You get this relentless stacking, filling up energy levels from the bottom up. This is what gives atoms their structure and, as we're about to see, what holds stars up.
Okay, so now we've got our key ideas. Nature's hunt for low free energy, and the two particle personalities, the loner fermions and the party animal bosons. Let's use this to finally solve our puzzles.
Let's go all the way back to that dying star, teetering on the edge of total collapse. What's stopping it? Well, the answer is a bizarre force that comes directly from the antisocial behavior of its electrons.
This is where it gets absolutely incredible. As gravity squeezes the star, it tries to force all of the electrons, our little fermion loners, into the same tiny space. But the Pauli exclusion principle basically slams on the brakes and yells, no way. The electrons are forced to stack up into higher and higher energy states. All those high-energy electrons create a powerful outward push, a quantum force we call Fermi pressure. And that pressure is strong enough to fight gravity to a complete standstill. The star is literally saved by this subatomic rule about personal space. Amazing, right?
Now, this quantum pushback isn't all-powerful. It has its limits. If the core of the star is heavier than about 1.4 times the mass of our sun,
a critical number known as the Chandrasekhar limit, then gravity just becomes too strong. Fermi pressure gets overwhelmed and the star collapses again, this time into something even crazier, like a neutron star or even a black hole.
Okay, so from dying stars to something you can see any day, let's tackle puzzle number 2. Why is the sky blue? This one isn't about fermions needing their space, it's all about the random, clumpy behavior of a crowd of air molecules.
So our atmosphere is just this huge, chaotic crowd of gas molecules bouncing around all over the place. Because of all this random motion, for just a split second, you get these tiny little patches that are a bit more crowded than the areas right next to them. Well, these temporary little crowds act like tiny obstacles for the sunlight coming in, and it turns out this scattering effect works way better on shorter wavelengths of light. So blue and violet light gets scattered in every single direction, basically painting the whole sky blue. Meanwhile, the longer red and yellow light just kind of punches right through, which is why we see those colors so clearly during a sunrise or sunset.
And finally, our chemistry puzzle. How do reactions know when it's time to just stop? This is all about a concept that's tied directly to free energy. It's called chemical potential.
A good way to think about chemical potential is as a kind of chemical pressure. It's a measure of how much the system's total free energy changes if you add or remove just one particle. And just like heat always flows from a hot place to a cold place, particles will always flow from an area of high chemical potential to an area of low chemical potential. They're always searching for that sweet spot of minimum free energy for the entire system.
So, what we call a chemical reaction is really just particles flowing from being reactants to being products. That reaction keeps going as long as that flow is lowering the system's overall free energy, and it stops when a perfect balance is hit, the moment the total chemical potential of the reactants is equal to the total chemical potential of the products. At that exact point, there's no more advantage to be gained by reacting, and the system settles into its happy equilibrium.
So let's just step back and pull this all together. It's pretty incredible, right? We've seen how just a couple of simple rules for quantum crowds can have these enormous, universe-shaping consequences.
This one idea really says it all. The same rule that forbids two electrons from sharing a state also prevents a star from complete collapse. Think about that. That one tiny, antisocial habit of an electron is what gives an atom its entire structure, and it's also the thing that holds up the gigantic remnant of a star millions of miles away. It's a rule that works on every scale.
So when you really get down to it, whether you're talking about the random clumping of molecules giving us a blue sky, the stubborn refusal of electrons to share space propping up a white dwarf star, or the delicate balancing act of chemical reactions that makes life possible, our universe is fundamentally shaped by the physics of crowds.
And that kind of leaves you with a final thought, doesn't it? We've only just scratched the surface here. So the next time you look up at that blue sky or think about the stars, just ask yourself, what other deep secrets of our universe are just hiding in plain sight, secretly being governed by the simple, unseen rules of the quantum crowd?